All right. Home stretch, one final talk, and then we go to happy hour. Um, Yay. Um, so for the final talk, we're going to talk about Android. And it's a really important topic as I was talking about in the keynote. And we have some people from Facebook here to talk about it. So we have Chris Mara. We have Tyler Keefe from the Instagram team, actually, and Andrew Rogers. So without further ado, I'll hand it off to Chris, who's going to frame up the issue and give you a ton of information on the Android markets. It's super interesting.
Cool. Hey, everyone. My name is Chris Mara, and I'm a product manager on Android at Facebook. And as Jay had mentioned this morning, we actually sort of shifted all of our development models around the company to say product teams own features. So instead of the Android team building photos, we'll have photos build photos. And we realized that there might be a slight flaw to this, and we still needed some people to really deeply understand certain platforms. So we've had a small group of us focusing very specifically on what's Android like, what's iOS like, and how do we really adapt to what the platforms are offering, and understand where they're going in the market. And Android as a platform has this really long, storied history. Used to have hardware buttons. We thought keyboards were going to be a big thing. Things have changed a lot. Screen sizes are like double what they used to be. So Android is really evolving. It's evolving quickly. This is just like 5 years of history. And even in that time, the official Google recommended phone has shifted a ton. And what we see on Facebook is even more dramatic than this. There's about 10,000 different device models that are accessing Facebook on a regular basis. That's way more than the Photos team can understand when they're building their latest feature. And there's no way that we would expect them to think about this and say, cool, yeah, I'll just have like 10,000 different versions of this that run differently on each phone. So we wanted to really step back and come up with a better way of thinking about the platform and making it easier for teams to understand. And anytime that a platform is growing like this, you need to ask some fundamental questions of who's the typical person using this. Are they on a high-end phone? Are they on a low-end phone? What country do they live in? What type of bandwidth access do they have? Because they're probably not like us. They probably don't have a high-end phone. And that's probably only the tip of the iceberg about really building the right product for them from a user experience perspective or from a technical perspective. So we sent people around the world, and in the past couple of years, we've sent research teams to tons of different countries spread everywhere, just to try to understand what's really going on in emerging markets and how these people are using their devices differently. So we had people go and buy phones, go to these mobile markets, understand how you buy a SIM separately from a phone. This transaction took place through a cage. We were buying like $400 worth of low-end Android phones. And they're showcased in a much different way than you might expect walking into a Verizon store. So everything about purchasing a phone in the developing world is significantly different. You're paying less. You're getting a different type of phone. Oftentimes, they're secondhand. There's so many differences, and I'm going to get back to that in a second. But we also just talked to people, and we asked them what their daily lives were like, how they used Facebook, why they bought their phone, what motivated their purchasing decision, how long they were going to end up keeping it for. Everything about how mobile plays a role in their lives. And when I say mobile, there's really only two things in the developing world. There's some feature phones that these people have been used to using for a very long time, don't generally have any kind of internet access, and there's low-end Android phones. And there's aspirational Samsung S5s that everybody wishes they could own, but some people haven't even heard of an iPhone, or they never see an iPhone ever because it's just too expensive for these people. So there's three big categories of drastic differences. The first one is just in the devices and phones that they're using. It's not new phones like we're used to. It's older generation technology and often second-hand phones. And they're paying, say, $100 might be a higher-end phone compared to our phones that start at $600 unlocked. So just very, very different phones. And the big thing to focus on here is second-hand and last generation, because that's what these people are really using. And so you can't assume that upgrade rates are naturally going to take care of things. Upgrade rates are going to be lagging significantly behind. The next element of this is data plans. Most people are on prepaid plans where they're loading up a certain amount of cash based on their latest paycheck. They may not get paid regularly, and that's part of the reason why. There's also been a struggle by carriers in developing countries to figure out how to sell data to people. It became relatively obvious in the US when the iPhone started taking off that we could sell megabyte and gigabyte based plans. But they haven't been able to make the same case in developing markets where the internet isn't necessarily a given. The idea that I want to access the internet may not be a pre-established fact. You need to prove to somebody that it is valuable for them to be on the internet. And so carriers are starting to explore things like time window plans, access the internet for a week, and they impose data caps behind the scenes and throttle your speeds, but they're selling it in a fundamentally different way because you need to show somebody that there is value in being connected to the internet from the thing that's in your pocket. The last one is cell networks, and this relates very strongly to the business model case. It's really expensive to spin up a cell network, and it's even more expensive when populations are less dense. So we're used to great LTE networks that are really well maintained, and AT&T and Verizon have strong competition, so they have strong incentives to continue upgrading these. That's not true in most places. There's barely 3G penetration. It's congested networks, and even Wi-Fi tends to be based on a slower landline connection where it happens to be available. And public Wi-Fi often suffers the same congestion issues. So everything about accessing the internet is a lot different in these types of markets. So we started thinking about which problems we could tackle that were tangible to a Facebook user. And these are the three big categories that I'm going to spend some time talking about. Slow phones, small screens, bad networks. The biggest of this is slow phones. And specifically thinking about the fact that with hundreds of mobile engineers around the company, how do we actually get teams to care about specific classes of devices? How do we make sure that people are optimizing for that low-end Android phone that you can buy for $60 in a mobile market instead of just a Galaxy S5? And how do we do this when, of course, there's 20 different teams doing it? So we came up with this abstraction called year classes and just ask in what year would a phone have been considered high-end, based simply on its CPU, its number of cores, and the amount of memory in it. Because that should be a reasonable gauge for performance and the type of performance that our app really needs. So the most popular devices, when you break it down by year class, give you a pretty cool picture. In recent years, it's mostly flagship phones. You notice that Samsung really dominates. But when you go back to 2010 and 2011, those phones weren't actually released in 2010 or 2011. They happen to have similar specs to it, but the LG Optimus L5 was released in 2012. It just happens to perform really similar to a bunch of other phones that are also dual core and also single core, also have 512 megabytes of RAM, and also have similarly clocked processor speeds. So this gives teams a small number of buckets to think about the way that their app is performing, and then we can start to cut all of our product metrics by it. So this is the % of weekly users who experience a crash inside of the Facebook app. You notice that it's pretty good in 2012 and 2013, but when you go back in time, it gets proportionally more crashier. The reason for this is because these phones had lower amounts of memory, smaller Java heap sizes, and we were causing out-of-memory errors. So it's a light abstraction on top of actual device specs that helps you drill into a problem, or just broadly categorize people into something that's easier to understand when you don't necessarily know where to be searching yet. And it lets us think about who's really the typical Facebook user, because 2011 is the largest bucket of phones. More people are running this low-end Android hardware, and we really need to stop calling it low-end. These are typical people. This is the average phone around the world. It is a dual-core phone with less than a gigabyte of RAM. So we've also started applying it when we're thinking about new product redesigns and such. This is a redesign of the comment flyout on Android. It's this really nice animation that you get to from feed. And when we first rolled it out, we noticed that generally commenting on the website was up. More people were engaging with this. They were opening it more often. Wonderful things were happening. We were ready to roll it out. Then we cut all of the metrics by year class. And we noticed that for people on low-end phones, it was actually a negative experience. We promptly unlaunched it to them while leaving it rolled out to just high-end users, and redesigned a version of it that used lighter animations that were more friendly on the types of hardware that those phones had. And we're able to launch a version of it that is functionally the same, gives you the same type of UI, but a slightly different animation and slightly tweaked experience that is positive for everyone. And we're starting to apply this lens to all of the experiments that we run and all of the features that we work on to make sure that even if we continue improving our aggregate metrics, we're not leaving anyone behind. And we're making sure that it continues to work on all types of phones. The next issue is screen size. And there's certain places inside of our application today that are relatively well designed. Newsfeed presents largely the same information. It has a little less space. It's very scrollable, and your default nature while using it is to scroll. So it's not in that bad of shape. Timeline completely loses functionality. It shows me a very blurry version of my cover photo and my name. And Events shows me no current events. To be fair, it doesn't on a high-end phone either. And it actually, don't worry, I'll redeem them in a second. It actually loses the plus button. You couldn't create an event on an LDPI phone for a while. And this is about 10% of the people that we see coming to Facebook who just didn't have this plus button because the menu bar code was designed to throw things out in order to have enough space for text titles. But nobody necessarily went and tested every edge case on every single phone out in the wild. So when you actually look at the screen size distribution, though, it's not like there's any specific part of it that you should just lop off and ignore. People on small phones are still out there. And admittedly, it's decreasing slightly over time. But we're really seeing people converge towards the 480 by 800 or HDPI bar as the most common screen resolution that Android has. Growth in the high-res buckets is also happening. But when you start to cut it by specific countries, you notice that there's going to be entire segments of the population that will always be on these lower resolution screens. And so that necessitates redesign. And it necessitates rethinking some of the assumptions in products and pushing our design teams to question the density of information, the importance of certain elements, and ways that we can provide the most important parts of each experience as quickly as possible. So now Timeline actually shows you the information that you need, gets rid of a little bit of Chrome, it gets rid of some of the less useful information of the cover photo, but you can still access it. And Events also reprioritizes everything that it's showing, moves its navigation switcher to be a smaller component. And again, we get rid of some of the overall application Chrome. So this just makes for a dramatically better experience for somebody who's on a very non-responsive touchscreen that's probably not going to be super accurate with exactly where they touch and don't have that much space. You need to get as much content above the fold as possible. The next thing, which Andrew's going to touch on a bunch more in a second, is just generally looking at connection speeds around the world and also starting to consider the cost of internet access around the world. In the US, there's about 70% 3G or 4G penetration. In India, that's 7%, and in Brazil, that's around 38%. So there's just dramatically different levels of connectivity, and even where somebody has the same level, the average latency is a lot worse. India is 500 milliseconds. There's actually an asterisk to that. It's because most of the country is on really crowded 2G connections. So their 3G is actually relatively high quality compared to what most people are experiencing. That's because 3G data access generally costs twice as much as an equivalent amount of data on 2G. So most people are being priced out of accessing that while operators are trying to recoup the infrastructure costs. But it's just really important that we can continue in all variables to consider these different scales and to consider the fact that not everyone is on a fast phone. Not everybody is on a fast network. Not everybody is on a large screen. And how do you make sure that the experience degrades at each one of those cut points? So takeaways. Android is the world's platform. Increasingly, it is becoming the first point of internet access for most of the population and will continue to be that way, whether it's Google Android or another form of Android. You are not like other people, and they're accessing the internet in dramatically different circumstances than you. And the way to make things good and acknowledge the way that the market is playing out is to segment smartly. And that applies both for making a good product and as an organizational tool. It's really challenging for us to go to every team inside of Facebook and say, you're doing this wrong, and you're doing this wrong, and you're doing this wrong, without also providing them with tools that help them do the right thing and help them be aware of how to look for the places where there's opportunity. Once we started showing teams graphs of how they were performing on different phones, everyone reprioritized their roadmaps. Because as soon as you see that you're 3 times slower on certain phones, you want to fix it. And so providing those tools is just as important as exposing the problems. And next up, Andrew to talk about some of these tools.
Thank you, sir. Good luck. Thank you, Chris. I'm Andrew Rogers. I'm an engineering manager in the Facebook Seattle office, and I work on our Facebook for Android application. As Chris alluded to, the network characteristics and the costs of network in other countries are not what you're getting here in the US. Today, I'm going to talk about changes that we've made to our Facebook application for Android to make it perform better on these different types of networks. We're going to cover 3 areas: image download sizes, dynamic network quality detection, and I will touch on prefetching content. First, reducing image download sizes. So the thing to note here is that image data dominates the bytes that we get downloaded to, or that we download in the Facebook application. It accounts for 85% of total data we download to Facebook for Android, and even 65% in Messenger. So clearly, if we're able to reduce the size of images that we download, we could save quite a bit of data. Not only that, smaller image sizes will result in quicker downloads, so the images end up on your device more quickly, especially on high latency networks. First, and most obviously, you can scale down your images on the server before you send them down to the client. Sending a large image to the client just to have it resize it locally to fit on a small screen is kind of pointless. It wastes a lot of data. It takes unnecessary time. Instead, you could choose to send smaller images, a thumbnail, a preview, and then maybe only a full image when the user actually needs to zoom in on it or share it over email or something like that. Many times users will never need anything more than just a thumbnail or a small preview. Oh, just to reinforce the scale here, this image is 960 pixels wide. The image of the kitten, that is. On top of that is a phone whose screen is 240 pixels wide. You'd have to pan around quite a bit just to see the entire kitten. So you might as well shrink it down. Still super cute. But the savings is significant. So scaling down a 960 pixel image to fit on this screen, 240 pixels wide, saves 86% in size. Even on a larger 720 pixel wide screen, which is also a popular size, you're still saving 23%. So image scaling can be a little bit of a balancing act here. Smaller files download more quickly, but if you download too many different sizes, you're going to end up using more data potentially. So if you had an image that was displayed in many different ways throughout your app, and you downloaded a unique image for each one of those instances of a different size, you may end up downloading more data than you did originally with just a single image. In the Facebook application, we've chosen 3 primary image sizes that we download per screen resolution. There's a preview image that we download, which is what you're going to see in your news feed. We'll also download a smaller thumbnail image for profile pictures and a larger one that you will see in photo stories. It's also worth mentioning that since screen sizes are generally getting bigger, it's trending that way at least, scaling images isn't as effective as it used to be. This is something we've done over the last year in Facebook app. It isn't paying off quite as much as it was at the beginning. Still worth doing. Another thing you can do is change the format of the images that you're downloading. So this table lists several of the popular formats. You might expect that in the Facebook app we would be using JPEGs for most of what you'd see in your feed. In actuality, 90% of the images we're sending to the Facebook app for Android use the WebP format. So WebP is a relatively new image compression format. It was released by Google in 2010, and it's really well supported on newer Android OSs. So why are we using WebP? In our testing, we found that it saves 7% download size over JPEG for equivalent quality test results. But by moving to WebP and by tuning the quality and compression parameters, we saved over 30% with the previous JPEG compression that we were using. And that's really significant when you think about it. In our testing, there was no noticeable change in user-perceived quality. Kitten again. This is a comparison of JPEG versus WebP. When I was putting this together, a couple of us were looking at it. We really couldn't tell the difference. Honestly, I couldn't choose which one I thought looked better. I pulled both of these directly from the Facebook servers. The one on the right is WebP. The one on the left is JPEG. See, I can't tell the difference. But the cost savings is pretty significant. It's over 25%. Another thing worth noting is that WebP supports other functionality not included in JPEG, like transparency and animation. These are things that we use in our stickers product, which you may be familiar with. We used to download stickers using PNG format, uncompressed. Switching to WebP saved 80% in the size there, which was fairly significant, as you can see in this sticker image. So I mentioned before that WebP is well supported on newer Android versions. We found that all the functionality we needed was only in Jelly Bean and newer, so Android 4.2. For older versions of Android, we're still downloading images in WebP format, but we include libraries in the application to transcode them on the client once they're downloaded. So we're still getting the cost savings, but we are transcoding to JPEG and PNG before we cache them and before we render them. If you do want to avoid the transcoding cost, you could do something different. You could continue to use JPEG, something like the Mo's JPEG 2 encoder. It's fully compatible with JPEG. You get better compression results with a pretty small, pretty reasonable reduction in file size. So decreasing image sizes is pretty significant, but we found that we really needed to have a way that feature developers working on the Facebook for Android application could know whether or not they were on a good network or a slow network. So before I get into the details, this graph shows network round trip times that from information that we gathered across four different network interfaces in 3 different countries, the US, India, and Brazil. So the thing that stands out most here, the US is the red bar, is that even on the exact same network technology, we've got 2G, 3G, LTE, and Wi-Fi, the connection speeds in the US are 2 to 3 times faster. I guess it's 2 to 3 times slower in the other. This is kind of interesting, though, because you'd think same network technology would have similar speed. Another thing that's interesting to note here is that the LTE connection speeds in Brazil and India, the other 2 countries here, are actually faster than the Wi-Fi speeds in those countries. So the details here, it points to the fact that you can't just base the connection speed on the network type that you're connected to. Android surfaces that information, but simply looking at that is not sufficient. So we wanted to dynamically monitor network quality in the client. We really wanted a tool that developers could use, a lot like your class, which Chris described, that would allow them to determine if the network was fast or slow. So we built this into the client. We measured the throughput on all large network transfers, which ends up being mostly images in practice. The Facebook servers provide a round-trip time delay estimate in the HTTP headers when they send back for basically every response. And the client maintains a moving average of these values and attempts to determine the connection quality. It then provides a rating: poor, moderate, good, or excellent. Those are the current values we're using. Those could change. Those values, poor, good, moderate, excellent, those are then provided to feature developers that are adding features to the Facebook application. And they can adjust their behavior accordingly if the network is slow. So some of the things that we're considering doing on slower networks, these are things we're investigating. Increasing the image compression. So I said before, image compression can result in smaller files, quicker downloads, use less data. Why not do it even more when you're on a slower network, and we know you are? Issuing fewer network requests in parallel, just so we don't saturate the network, and the requests you have out there will return more quickly. Disabling features like autoplay video, things that won't work very well on slow networks, and also prefetching more content. I'll touch on that in just a minute. So that's good, but we're still all here in Silicon Valley. We have fast LTE connections, or we're on Wi-Fi at work. How do we know this stuff works? How do you actually test your features out? How do you test your app out on a slow network? So we've built an internal tool at Facebook called Air Traffic Control, and it lets developers configure their local Wi-Fi connection to emulate different network conditions. So we have predefined profiles that developers use to simulate connecting in a different country. You'll see here an example. We have a rural and an urban profile, different for India, and we have Brazil. There's other profiles here as well. And they're fully configurable. Each of these profiles is configurable with the bandwidth, the round trip time delay, packet loss, separately configurable for the uplink and the downlink. So we found this to be extremely helpful in basically finding unexpected behavior in your application when it's on slow networks. So before I wrap up, I want to briefly call out some of our learnings on content prefetching. So when I say prefetching, I really just mean issuing network requests for content ahead of when they're actually needed on the device. So we know that prefetching content is especially important on networks with high latency. If you wait to kick off a download request for an image, for example, if you wait until the viewport that's going to display that image is in front of the user already, and you're on a network with a high latency, say a second or more, the user's going to be staring at a blank screen for quite a while. So if you could somehow get that prefetch request out early, have the content there before the user saw the view, or at least a little bit ahead of time, they'd be waiting less to see their content. One thing that we do in the Facebook app is we issue our network fetch request for the feed early during startup. This allows us to parallelize waiting on the network with other initialization that happens while the app is starting. Other things to consider with prefetching, well, you don't want foreground network requests to be blocked on background network requests. If you're prefetching a bunch of stuff and saturating the network, you could actually make user responsiveness worse. So consider having some sort of a priority queue where the network requests for your foreground experience get serviced ahead of those for the background or for prefetching. Also, you need to carefully monitor for overfetching and just use of device resources. You could fill up the disk. You could end up wasting a lot of the user's data plan. As Chris said, this costs people money. Basically, things that you should consider when you're prefetching. In summary, scale your images down to an appropriate size before you download them. Consider alternative image formats and tweaking compression and quality knobs to have a result that you're happy with and to make the download size as small as possible. And even adjust your app behavior on slower networks. Like we've said, networks outside of the US can be 2 to 3 times slower than what you are used to using here. And with that, I will hand this off to Tyler, who is going to talk about Instagram. Thank you.
Hey everyone, my name's Tyler. I work on the Instagram Android team. I'm going to talk about some of the ways that we've improved Instagram to work on these lower performance phones, smaller screens, in emerging markets. We'll cover 2 things today. The first is design. So we basically rewrote our entire app UI this year, focusing on performance and on better performance across the wide range of screen sizes that we see on Android. And cold start. How did we get our app to start up super fast so that people on low-end phones have a great experience when they tap the Instagram icon? So we'll start by talking about design. This is what Instagram looked like when we launched. This was a little over 2 years ago. April 2012. And so for a little bit of history, the app was built by 3 people, a really small team, 2 engineers and 1 designer. And it was built in a little over 4 months. A really fast timeline. People were clamoring to have Instagram on Android, so we wanted to get it out to people as fast as possible. And actually, the entire Instagram team was really small at that point, less than 15 people. And so really, to keep things simple, to be able to get Instagram for Android out really fast, we basically kept the same design as the iOS app at the time. And we actually really only had 1 designer on the team, so it kind of made sense. And this is what the iOS app looked like. You can see it's pretty similar. This is the era of iOS 5, luscious gradients, lots of UI. As most of you know, Apple has since moved on. They introduced iOS 7 and brought flat design to the world of mobile, or at least to the world of iOS. Other platforms had similar things, but Apple did it in a very unique way. And we updated our app for iOS 7. And you can see how much simpler it is, right? Basically stripped out all the UI, took out all these boxes, no more gradients, no more shadows. It's a lot simpler. It's a lot more beautiful to look at. And from this experience of adapting the app to iOS to flat design, we took away a couple learnings. The first was that flat design is great for developers. It's really an opportunity to do less and to write code faster. You're writing less UI, and so you're going to be able to ship products faster. The second one is that it's a lot more performant. At the same time that you as a developer are doing less, the phone is doing less to display your UI. And so we wanted to bring these learnings back to our Android app and to really update that for the modern ecosystem of flat design. And so we decided to embark upon a redesign project at the beginning of the year. And our goal is really to simplify and polish what we already had. We didn't really want to change the app drastically. We didn't want to rewrite the navigation pattern or move stuff around. We just wanted to take what we had and make it more beautiful and more performant. So yeah, we had 3 goals. The first one was to make it flat, and by doing so, make it faster. And we'll talk about the ways in which we did that in a couple minutes. We wanted to be more screen space conscious. So as Chris talked about, there are so many different screen sizes. And we knew our app worked well on some of them, and different parts of the app worked better than others at adapting to the screen size. We really wanted to take a fresh look at every screen in the app and say, how could we better adapt this to all the different screens that are out there? And the third thing is we wanted to make it beautiful. This really underlies everything we do at Instagram, and that was an important part of what we did. So I'll show you some before and after pictures. A lot of these are going to be somewhat similar concepts as what Chris talked about with the Facebook for Android app. So this is the before and after, the main feed when you first get into Instagram. This is the first screen that most people open up onto. And there's a couple things I'll highlight on this slide. The first is that we basically took everything out of the Chrome. We took all the gradients out, all the glossy buttons, all the shadows, and we're left with solid colors and flat shapes. And the second thing is that for the comments, we took out the little comment icon and made the comments the full width of the screen so that there's less UI. People on really small screens have more room to read the text. And the overall effect is one of just dramatic simplification, right? On the left side, the Chrome is kind of garish. It stands out. It really distracts your attention away from the beautiful photos that we want you to be looking at. And so we want our UI to fade into the background. We took away, we went to outline shapes instead of gradient buttons for the icons, and really just tried to make the content the primary thing on the screen. Second thing we looked at was the creation flow and editing flow. So when you take a photo or take a video and then edit your photo or video, the layout on the left is really actually optimized for the smallest of screens. It doesn't work well on medium or large size screens. And that's because all your controls are at the top of the screen. So for the camera, things like the switch camera button, and in the editing flow, your filter controls are often at the top of the screen where they're not easily accessible for your thumb. And so we actually forked our layout here. On really small phones, we still do the layout on the left, but on medium phones, such as the 480 by 800, that's the most popular screen size, or even larger phones than that, we actually bring the buttons down to the bottom. And so it results in a dramatically better experience because you don't have to be touching buttons at the top of the screen. We found small optimizations all over the app. our goal was to remove unnecessary UI and give more of the pixels over to content. So on the search screen, we discovered why have 3 layers of Chrome here. We can take the search bar and move it into the title bar and really collapse it down to 2 layers. So on a really small phone, you're getting a lot of space back, especially with the keyboard up to view content. And lastly, our old friend, the Galaxy Y. This phone is really amazing. If you've never seen one of these, you really ought to get one. It's unbelievable what your app looks like on this thing. And this screen is so small. It's 240 pixels wide. And we looked at the old design on this, and we said, wow, there's a lot of the screen that's being taken up by the tab bar and the title bar. Is there any way we can do better? And it was a lot easier to tweak these UI components when they were just solid colors. We can just adjust the height of elements. We don't have to cut new assets for gradients. And so when we did the redesign, we decided to try slimming it down. And we had the phone right there, and we tested it out. And it was just as usable. The tap targets were big enough to use. And as you see, we get 20 to 30 pixels back on that photo, which is really nice. So why flat design? I said it was performant. Now I'm going to try to prove it to you. One thing you can do that's really great if you have a flat design is you can do asset tinting. So in code, take this gray heart shape and turn it into a red heart. This is actually being touted as a new feature in the latest Android release, which is Android L. Not even out yet. It's out as a preview. But the big secret is that it's actually possible in all versions of Android shipped up until this point. And it's also possible in iOS. They give you this class called a color filter, which you can apply to a drawable or an image view. And specifically, we use a Porter-Duff color filter, which is designed to, you can actually do most of the different Photoshop blending modes. We use it in a much simpler way. We use it to just turn shapes that have alpha into other colors. Why would you want to do this? Why would you want to tint your assets? The first thing is that you're going to end up shipping fewer assets. If you have assets with different states, pressed states, selected states, you don't have to ship those anymore. You ship one shape. And your APK size becomes a lot smaller, which is great if you're on a slow network. You don't want people to wait to download your app. You want to ship the smallest app you possibly can. The second thing is that you're going to load fewer assets. So your UI is going to display faster, and you're basically using less memory to store these bitmaps in memory. If you think about it, when you start up your app, every asset that you're going to display on screen has to be read off of the flash memory and decoded into a bitmap. And the less that you're doing that, the faster it's going to be. And I'll talk about the numbers in a second. The last thing is that you really have faster iteration times. If you want to change the colors in the app, or if you want to do new development and you already have the assets there, you just need them in new colors. You don't have to put files in the app. You don't have to talk to a designer. You just have to get a color value and recompile, which is really, really nice. So yeah, this is what Instagram went from before the number of assets we had to load to display our UI to after. You can see we had to load 29 different assets to display just the tab and the title bar. This is different states, pressed states, unpressed states, gradients, basically the lot of it. And then afterward, we had 8 assets that we needed, basically just the shapes to display the icons and the Instagram logo. And everything else is drawn in code as solid colors and rectangles. And that actually shaved off 120 milliseconds off of our cold start time, just doing that. And that was really awesome. You'll see how that relates to our overall numbers in a little bit. And this is just the cold start impact. Really, the entire app got faster. Every screen, we were doing less. We're loading less assets to display that screen. And the whole app just felt like it got peppier when we were done with its redesign. And that actually got reflected in the user reviews as well. People said they loved the design. They said it felt fast. People really, really liked it. And I think I took a couple things away from this. One is that people understood the speed gains. The second is that people love it when you actually take your app and design it appropriately to fit the platform that you're on. And yeah, it was a really good, awesome result. So we'll talk a little bit more about cold start now. We talked about cold start in relationship to asset loading. We'll talk about some of the other things that we did to get our cold start way down. Let's start with the numbers. So about a year ago, Instagram 4.2.4, this was our cold start times on one of the lower end phones in the market and one of the most high end phones. I just tested these numbers the other day. with an older version of the app. These are pretty good numbers, right? This is pretty fast, but a year ago, we were like, we can do better than this. And so over the past year, we've cut these down in half to the point where our app starts up in 1.5 seconds on a Galaxy Y phone and under ½ a second on an S5. And I should mention that this is the time for the app to start up and become responsive. You can actually use the app at this point. This is from tapping the icon to I can click around the app and it works. And the great thing about this, especially on these higher end phones, is that the app basically starts in, it's imperceptible, the cold start difference to the warm start. So you really can't tell whether Instagram's starting from scratch or it was already in memory. And even on a Galaxy Y, this is, Instagram is one of the fastest apps to start on the phone. So how did we get down here besides removing all the assets from our UI? You got to profile the app, right? You got to figure out what is slowing your app down. And there's 2 basic ways you can do this. You can do method tracing, so you can use Android's trace view tool, or you can put timing statements in your code. Both of these methods are a little bit fallible, so method tracing will tend to overcount the time caused by smaller methods just because of the overhead of logging when a method starts and stops. Timing statements, because you're measuring wall clock time, you're not really measuring time on thread. So if your threads are swapping in and out, you kind of get an imperfect picture of what's going on. But if you use both these methods and your intuition, you can get a pretty good idea of what's slow. And after that, you want to fix it, right? You want to take whatever is the slowest thing in your app and fix it. So you can either remove it from the cold start path, lazy load it. You can rewrite slow code. So one example of that is we had some slow JSON parsing code that we rewrote to be faster. Or you can defer things to a background thread. So if you're doing stuff on the UI thread that can be done in the background, we want to do that as well. And then once you do that, you want to go back to step 1 and start over again, figure out what's the next slowest thing, and keep going and iterate till you get your cold start to the time that you really want it to be. So when we did this, we used the timing statements to find out that we had a lot of really heavy singletons in our app that were causing a lot of our initialization time. We were initializing these all before the app could start up, the HTTP client, the image cache. And our great realization here was, well, we don't really actually need an HTTP client or an image cache to show the app UI and to have the app start up and be responsive. We can kind of load those in the background in parallel. And so we came up with this method that we call 2-part lazy loading. 2-part because we want to initialize these objects lazily, but we don't want to break the programming contract of a singleton whereby it's always available to the app. We don't want to have people that are writing code have to check whether or not the image cache is initialized yet, because that would make the code complicated and brittle. So what we do is we create the object on the UI thread. We create the object enough so that its public API is intact and any developer can use it. And then we defer the hard work to a background thread. So in the case of the cache, this is opening and reading from disk storage. For the HTTP client, loading certificates off the disk to be able to do SSL, cookie store, deserializing cookies. And that basically makes the UI appear on screen much faster. We're deferring hard work till later, but we didn't mess up the programming model of having these nice, simple singletons around our app. For an example of what we found out through method tracing, this is an example trace of the cold start of our app from a few months ago this year. And one thing that we noticed that really surprised us is that about half these threads came from a single web view in the app, our news view. And the news view is the page in Instagram that shows you all of your likes and comments. And it was originally written as a web view. We thought that we'd want to be able to ship updates to it faster than we were shipping the Instagram client. And now, it was a product requirement that we load this view at startup. So when you load Instagram, we want to show you this, how many new likes and comments you have, right? That's the most exciting part of using a social network is interacting with other people. So we pop up this little orange bubble. It says you have 5 new likes, 10 new comments. And then once you tap on that, we want to be able to immediately show you this expanded view. Well, unfortunately, the web view, really, you have no control over it, right? It has its own network stack. It has a separate image cache. It's going to do whatever it wants when it wants to. And as an app developer, I really have no control over that. So we took the hit. We converted this to native. It took probably 2 to 4 weeks. This was not an easy thing to do. There's a lot of different types of stories in this view. But after the native conversion, we saw that there was a 30% drop in cold start time across all versions of Android out in the wild. This is from data out in the wild. So what are the lessons learned? Fast cold start times are achievable. We thought our cold start times were really fast about a year ago, but then they got even faster. And this was through profiling and diligent profiling of the code. And I'm not telling everyone to remove web views out of your app. You got to profile your app and figure out what's slow about it. Using pixels judiciously. This is really, really important. People in other countries are using dramatically smaller phones than we are here in the US. And it's really important to evaluate every piece of UI you have and whether it makes sense or not on screen. And lastly, mobile phones love simple design, and also mobile developers do too, because it's a lot easier and it's a lot faster. So that's it. Thank you.
So Chris, Andrew, do you want to come up? So we have time for Q&A. So any questions you have back here?
Those lights are so bright.
They're so bright.
Yeah, so you talked about emerging markets, but in, say, Japan and South Korea, you actually have much faster. So the opposite part of it, do you do anything special to actually make the experience much better on amazing networks?
I think in general, we have pretty fast Wi-Fi at the office. I think it's fairly easy to get a great experience on fast networks just because those are the networks we're so used to. I think really the difficulty is optimizing for those slow networks. Now, not at the expense of a great performance on Wi-Fi. That's where it becomes really difficult. Is you want the app to be great in both situations.
And frankly, I think that fast connections are simply able to mask areas where we have optimizations that we need to make. So one of the things that I notice when we're on our office Wi-Fi is that the fact that we're issuing a ton of concurrent requests in the application without thinking about how much our actual upstream pipe has available doesn't impact performance, and it does in other places. So the optimizations that we're making can really apply to any connection speed, and when you start to go in and add actual prioritization, make sure that you're bumping up things as soon as they enter the viewport, those things all still matter for high-end connections. And we're also thinking about the fact, hey, if you look totally unconstrained on bandwidth, maybe we should serve you slightly higher quality images. Autoplay video is a feature that we have rolled out for people on different connection types now, and we tune that for different countries as well in order to make sure that we're respecting the availability of a pipe.
That's why we have that excellent grading at the high end of the rating thing. So yeah, definitely something we're thinking about.
I was really interested to hear about all the optimizations that you did for loading images, especially on limited phones and slower networks. I was wondering if you had projects like that for uploading images and uploading content to a network also.
We did a ton of optimization in this, at the end of last year as well, on upload reliability for photos in both the Android and iOS apps. The biggest lessons learned were aggressively retry when there's a failure. A lot of the times that we would find that failures were, at this point, most of our failures are really just something wrong with the pipe and they fail immediately. Anytime that something doesn't go through midway, we just start retrying. The other really important thing for image uploads has been client-side resizing and encoding. So instead of sending a 2 megabyte photo, we, in the past, would at least do recompression on the device. Now we also do resizing on the device, which in certain instances also saves server transcoding costs because we already have a pre-compressed image. So the main lesson there is just fewer bytes over the wire and retry, retry, retry.
All right, there's a question that you use WebP on Android. Have you used WebP on iOS, and what's the experience for that?
Just on Android at this point.
I have one question regarding the
I'll get you in a second.
So my question is so with images, you guys resize it. Did you guys apply anything similar to video?
I don't know exactly. On video right now, we've got a couple different compression qualities and a couple different resolutions that we re-encode to. The short answer with images and video is that we're doing transcoding on the server for both quality and resolution. I forget exactly which bucket sizes we picked for video. There's slightly fewer, but it's increasingly becoming a larger part of our app experience. So we're figuring out what better encoding technologies we can use now, and whether we need more whitelisted sizes to be able to select a smarter one for each client.
We have 2 buckets for video on Instagram and 2 buckets for images as well as thumbnails.
Hi. I just wanted to know, do you do any A/B testing in the emerging markets to get the feedback?
So we do A/B testing on pretty much everything that we roll out, and we don't tend to gate things specifically to certain regions at this point. Most of our optimizations we want to work for all billion people, and then we do a lot of analysis to make sure that we're understanding the impact in specific areas. So we do occasionally find that product changes perform different in certain regions, and have like a general understanding of how certain regions behave differently in terms of engagement usage. So we don't often roll things out on a specific basis like that unless there's a really specific local need, but we're super careful in the analytical stage of looking at an experiment and making sure that it's positive for everyone and not like secretly negative for one group, but up for everyone else.
I have a question about the performance and whose responsibility it is. I noticed that you talked about different feature teams and make sure they understand the impact of some of the things. Is it each vertical is responsible for monitoring performance, or do you have a central team dedicated to monitoring all of that?
I'd say we actually sort of have both. Yeah, teams would be responsible for the performance of their individual features end to end, but we do have kind of some core teams across mobile who do spend a lot of time analyzing performance, looking for where issues are, and helping other teams with the issues that they find, and they have a lot of expertise in optimizing things.
We've gone through different approaches here too. Like, I'd say it's sort of recent that we have both teams caring about everything. A playbook that's worked well in the past for speed on the www side of things for us was having a core team and infrastructure that helps coordinate general performance problems, and is really good at doing instrumentation, identifying where problems are, and working with product teams in whatever capacity is needed in a specific case. But we're also finding, specifically on mobile, that it's really important each team own both their core engagement metrics, but their core reliability and performance metrics, data usage, how fast their feature starts up, reliability for their product, whether it's causing any specific crashes or something. So having the people who are really good at the playbook and understand how to go look, diagnose, and fix certain problems, in addition to making sure that every team is owning their full product end to end and making sure that they know how to and are incentivized to fix problems on it, I think both are really, really important at our scale of organization.
I have a question about how you publish the app, or actually whether you have multiple versions of the app depending on the device.
I think we publish like 20 different APKs for the Facebook app. They're cut by API level, screen size, and processor architecture.
Yep. Similarly for Instagram, we do the same thing.
Hi. I have a question on the original image source. Let's say, do you have the single image what you share across iOS and Android? And the second question is, let's say the full image needs to be displayed and this is low resolution device. Do you kind of know about that in advance and you're minimizing the image size, you're kind of scaling it on the server side?
So on the server, we have multiple resized copies of the different images. And we tell the client about the different sizes that it has available. And so it is up to the client to decide which size do I want to pull down for whichever view it's rendering. So the images would be shared across platforms. So the iOS client would be downloading same images as the Android client with different sizes depending on the different screen size. And I'm sorry, what was the last part of the question?
The second question is, let's say the original photo was done on a high resolution camera.
Sure.
And you're loading this on a low end device. So, and you want to see the full image, right? So would you kind of evaluate the capabilities of the phone and based on that don't send, let's say, huge image to the device which is practically not capable in display?
Right, yes. Yeah, we would send a smaller version basically for smaller screens.
One last question here.
Hi, I would imagine to support different networks, in emerging markets, you guys would do a lot of caching. Can you tell us about a little bit more about your caching stack? Did you go for any open source projects, or what are the challenges you faced building it?
Which level of caching?
Say not at the HTTP cache, but at a higher level. Say you want in the morning we're talking about iOS, where we're talking about more model layer, immutable models, and component level caching. What is the equivalent on Android?
I don't think I have enough to talk about that here. Come grab me afterwards in happy hour and let's chat. And whoever asked the question about WebP on iOS already tells me that I lied about that. So we have done some WebP on iOS stuff. I'm not familiar with it.
So ask Ari about it.
Yeah.
On that note, let's give one final applause to our speakers here. I think it was fantastic. And I'd just like to thank all our speakers. You know, everyone put in a ton of effort, and I think it shows. And so we are done. I hope you guys found it as useful as I did. And why don't we put that URL on screen? Just a reminder, this is the Facebook group. We're going to try to make it as active as possible. We're going to post all of the videos, and the speakers will be active there answering questions. So thank you all for coming. There's a happy hour now on the 4th floor, and please join us. And thank you for coming to AtScale.